800 meters. That's the entire runway. Dirt, uneven, edges, riddled with mortar craters. Under normal circumstances, no pilot would agree to land a 70-ton aircraft on this strip. But this was not a normal place. The 7th of March, 1968, Khe Sanh, combat base, South Vietnam. The base was under siege. The ground route had been cut off. For the 6,000 soldiers inside, the only supply line ran through the sky. At 4:47, a sound of engines rises through the darkness. Low, steady, approaching. A C-130 Hercules lines up with the runway. Wheels touch the dirt. 4 turboprop engines go into reverse thrust. The aircraft stops before reaching the halfway point of the strip. The rear ramp opens. 9 minutes. Ammunition, food, medical supplies all unloaded. The ramp closes. Engines go to full power. The Hercules lifts off the dirt and disappears into the clouds. The entire operation took 13 minutes. That aircraft would land at Khe Sanh 6 times that day, and it would come back the next day, and the day after that. How can a 70-ton machine land on an 800-meter dirt strip? The answer lies in the story of the most durable aircraft in aviation history. The story of the C-130 Hercules begins in 1951 with a set of technical specifications published by the United States Air Force. The need was clear. The military wanted a new transport aircraft that could land on unprepared runways, carry heavy loads, and serve in both tactical and strategic missions. The aircraft in use at the time, the C-119 flying boxcar and the C-123 Provider, couldn't fully meet these requirements. Their range was limited. Their payload capacity was insufficient. Their maintenance demands were straining the field crews. Engineers at Lockheed prepared an answer to these specifications. A small team, led by Chief Engineer Willis Hawkins, designed a 4 turboprop, high-wing, wide-body cargo aircraft. Hawkins' team wasn't working with the vast resources of a large corporation. It was a small group, a tight schedule, a clear objective. Sometimes, the best designs come out of exactly that. The first prototype took off from Lockheed's factory in Burbank, California, on the 23rd of August, 1954. Test pilots Stan Belts and Roy Wimmer took the aircraft into the sky for the first time. The flight was successful, but the real test was still to come. The Air Force began testing the aircraft on unprepared surfaces, gravel strips, muddy terrain, ice-covered ground. The Hercules took off successfully from every single one. Engineers pushed the design limits, maximum load short runway takeoffs, single-engine failure landing procedures, airframe stress tests under extreme payload conditions. Every time, the results exceeded expectations. In 1956, the C-130, a model officially entered service. Lockheed's engineers knew something from the very beginning. This aircraft was not designed as a war machine. It was designed as a system, transport, delivery, connection. Wherever needed, under whatever conditions. They built that philosophy into every millimeter of the aircraft. The strength of the C-130 comes from the simplicity of its design. The fuselage is built on a flat cargo floor. The floor sits just 130 centimeters off the ground. No forklift needed. No crane needed. A truck can drive directly inside. The cargo bay is 12.3 meters long, 3 meters wide, and 2.7 meters tall. It can hold 6 standard cargo pallets, 92 fully equipped soldiers, or 3 Humvee vehicles. The roller conveyor system on the floor allows heavy loads to be moved with minimum effort. An experienced loading crew could fully load a cone 130 inches under 20 minutes, given the right conditions. The rear ramp is the aircraft's most critical engineering detail. It can open both on the ground and in the air. It makes parachute cargo drop operations possible. It cuts loading and unloading times down to minutes. When the ramp opens, the wind rushing into the cargo bay roars in the ears of everyone working inside. Loadmasters were so accustomed to that wind that they said when the ramp was closed, they felt like something was missing. The wings are mounted on top of the fuselage. The high wing configuration provides two things. The engine propellers stay far enough from the ground, minimizing foreign object damage on unprepared runways. And because the wing spar runs over the top of the fuselage, the cargo bay has no obstructions. The landing gear is designed to withstand short and hard landings. The main gear is arranged in a tandem configuration with dual wheels. This setup keeps the aircraft from sinking into soft ground. But what truly sets this aircraft apart are the 4 Allison T56 turboprop engines mounted on its wings. Each engine produces approximately 4,600 shaft horsepower. They spin 4-bladed propellers, propeller diameter 4.1 meters. The choice of turboprop was deliberate. Jet engines are efficient at high speed, but weak in short runway performance. Turboprop engines produce high thrust at low speeds, critical for short runway takeoffs. They also consume less fuel than jet engines. This meant the aircraft could carry more cargo on long missions because the weight saved on fuel could be filled with payload. The reverse thrust system works by turning the propeller blade pitch angle to negative. After landing, the pilot engages reverse thrust, and the braking distance is cut in half. Each engine module is designed to be replaceable in field conditions. You can remove an engine and install a new one in 4 to 6 hours. No hangar needed, no forward base needed. On the edge of a desert airstrip, under the sun, a handful of technicians could do the job. And they did, soaked in sweat, burn marks on their hands, sand in their eyes. Because the aircraft needed to be airborne again in an hour. Nobody complained. Everyone knew if that aircraft couldn't take off, someone somewhere wouldn't receive the supplies they were waiting for. Fuel capacity is approximately 26,000 liters in wing tanks. Range with a full load, 3,800 kilometers. But range was never the primary concern. What mattered was being able to reach anywhere. The most remarkable feature of the T-56 engines was their reliability. They could operate in conditions from scorching deserts to Antarctic glaciers. Sand filtration, anti-icing, lubrication systems, all designed to keep the engines running in the harshest environments. With regular maintenance, a T-56 could log tens of thousands of flight hours. The cockpit of the early C-130 models was one of the most demanding workspaces in analog aviation. Captain on the left, co-pilot on the right. Between them and slightly behind, the flight engineer. In the early models, there was also a navigator. The instrument panel was covered with hundreds of dials and switches, separate RPM gauges, turbine temperature gauges, oil pressure, fuel flow for each engine. The flight engineer was constantly scanning all of these parameters. His eyes jumped from one gauge to the next, reading the numbers, comparing them in his head. A needle drifting half a dial from normal, noticing that was his job, for hours, without pause. The flight controls were mechanically linked to the surfaces by cables. There was hydraulic assist, but the primary control was mechanical. The pilot felt the force directly through the control column. Every shift in the wind, every jolt of turbulence passed straight through to his arms. There was no automation in this cockpit. Every decision was made by a human. Every parameter was read by human eyes. And these humans got tired. On a 12-hour mission, the engine noise blended into a constant drone, the kind of drone where crew members could barely hear each other, even when shouting. The vibration seeped into their bones. In unpressurized models at high altitude, oxygen masks were worn, and sweat pooled under the mask. The navigator hunched over his charts, calculating star angles, because there was no such thing as GPS. The loadmaster was in the cargo bay, checking the tie-down straps, because a poorly loaded pallet could shift the center of gravity in flight and send the aircraft out of control. 5 people inside a metal tube, thousands of meters above the ground, for hours. When the crew stepped off after a mission, you could see it in their faces. Dark circles under their eyes, shoulders slumped, speech reduced to monosyllables. Nobody talked on the walk to the mess hall. The silence was a shared ritual. A few hours of sleep, then back to the briefing room. Operating under these conditions required far more than knowing the aircraft. It required knowing each other, hearing that slight edge in the captain's voice, noticing the flight engineer scanning the gauges faster than usual, recognizing that when the navigator furrowed his brow, something didn't add up. Reading these signals that was never written in any training manual. October 1960. McMurdo Station, Antarctica. A C-130 Hercules, fitted with skis, sits on a glacial runway. The LC-130 variant, ski wheel combinations, mounted in place of standard landing gear. The U.S. Navy's VXE-6 squadron used these aircraft to ferry supplies to scientific research stations across Antarctica. The conditions were merciless. Minus 40 degrees, winds at 60 kilometers per hour, visibility down to a few hundred meters. Before starting the engines, specialized heating units were hooked up to the cowlings. The oil had frozen, the hydraulic fluids had solidified. At least 2 hours of preheating, during which the technicians huddled beside the metal fuselage, bracing against the wind, fingers going numb inside their gloves, face masks icing over with every breath. But the aircraft had to be readied. A research station was waiting for supplies. The takeoff procedure was different too. The skis could freeze to the ice. The pilot would fire the JETO rockets, solid fuel rockets mounted to the fuselage. Once ignited, they broke the aircraft free from the ice within seconds. The Hercules would lift off, below it, an endless white expanse. This aircraft would go on to become the first wheeled aircraft to land at the South Pole. In the years that followed, LC-130S made regular flights to Antarctica's most remote outposts. On some missions, pilots had to land in a white void with no reference points whatsoever, no horizon line, no shadows. Depth perception vanished entirely. Pilots called it whiteout. The radar altimeter measured the aircraft's height above the ground, rate of descent, propeller pitch setting, engine power. Every parameter demanded a precise balance. A single mistake could put the aircraft at risk of slamming into the ice surface. Pilots had to ignore everything their eyes were telling them and trust the instruments. That meant going against the most basic human instinct, but they did it because a handful of scientists stranded on a glacier were waiting for food and fuel. The real test for the C-130 came during the Vietnam War, and something needs to be said plainly here. This aircraft didn't just carry food and medical supplies. It carried ammunition. It carried bombs. It carried napalm. The AC-130 Spectre variant was converted into a direct combat aircraft firing on the ground from cannons mounted to its side. It sat at the center of the logistical chain that kept the war going. Every successful C-130 delivery meant another day of fighting on a front line. To tell the story of this aircraft while ignoring the fact that some of its cargo was destruction would be dishonest to history. But what happened at Khe Sanh needs to be seen in full too, because the same aircraft, on the same runway, on the same day, was delivering both ammunition and evacuating the wounded. The paradox of war was made tangible inside the cargo bay of this aircraft. During the siege, ground access to the base had been cut off. The soldiers inside faced starvation and ammunition shortages. C-130 pilots approached at low altitude, landed on the short dirt strip, unloaded cargo in a matter of minutes, and took off immediately. The runway was under fire. Aircraft took hits but kept flying. The crew in the cockpit could hear the metallic clatter of rounds striking the fuselage. The co-pilot swallowed hard when he saw mortar explosions along the edge of the runway during approach. But he didn't take his hand off the control column. The LAPE system was one of the most dramatic cargo delivery methods. Low-altitude parachute extraction system. The aircraft flew just meters above the runway, rear ramp open. A parachute attached to the cargo pallet deployed, and air resistance pulled the cargo out of the aircraft. The pallet slid to a stop on the strip. The aircraft never landed. It never lost speed. It just passed over. Parachute cargo drops were also used. While the C-130 flew at medium altitude above the base, pallets were released in rapid succession from the rear ramp. Each pallet had its own parachute. Soldiers on the ground collected the pallets and carried them back to the trench lines. Pilots flew these missions multiple times a day, sometimes every time. The same runway, the same line of fire, the same risk. Every pilot who climbed aboard looked at the hole from the hit taken on the last run and said a quiet prayer that a new one wouldn't appear. The siege lasted 77 days. C-130S delivered over 12,000 tons of supplies. Many aircraft took hits. Some sustained heavy damage, but the operation never stopped. Even with one engine gone, the aircraft could return to base on the remaining three. Despite bullet holes in the fuselage, it maintained structural integrity. War was not the only face of the C-130, and perhaps the face that mattered more over time began after the fighting ended. Wars end, but disasters don't. In 1970, a cyclone and flood disaster in East Pakistan, present-day Bangladesh, affected hundreds of thousands of people. Roads had been destroyed. Airports were damaged. C-130S were among the first relief vehicles to reach the area. They landed on short and damaged runways. They carried tons of food, water, medicine. The same cargo bay that had carried ammunition just months earlier was now carrying sacks of rice and water tankers. The aircraft was the same. The mission was different. This pattern repeated. The 1985 Mexico City earthquake, the Kurdish refugee crisis after the 1991 Gulf War, Somalia in 1992, the 2004 Indian Ocean tsunami, the 2010 Haiti earthquake. Every time, the C-130S were there. More often than not, they were among the first aircraft to arrive. In disaster zones, conventional airports were usually unusable. Runways cracked, control towers collapsed, fuel systems damaged. Most aircraft can't land in these conditions. The C-130 could, because from the very beginning, this aircraft wasn't designed for perfect conditions. It was designed for impossible ones. In Haiti, after the 2010 earthquake, the runway at Port-au-Prince Airport had cracked. The control tower had collapsed. In the first days, almost only C-130S could land and take off. 20 tons of relief supplies per flight. Land, unload, take off, return, over and over. The same crew, the same aircraft, multiple runs in a single day. The pilot's sleep hours weren't worth counting, but every ramp that lowered meant someone would survive another day. The aircraft's role expanded over time. A firefighting version responded to forest fires, dropping thousands of liters of water from tanks under the wings. An air ambulance version transported the wounded. A weather reconnaissance version flew into the eyes of hurricanes to collect data. The basic airframe stayed the same, but a different configuration could be created for each mission. The C-130 was no longer a single aircraft. It was a platform. The C-130 Hercules didn't remain solely an American Air Force aircraft. It was delivered to the air forces of more than 70 countries. The United Kingdom, Australia, Japan, Saudi Arabia, Turkey, Brazil, Indonesia, and dozens of other nations added the aircraft to their inventories. Each country used the Hercules according to its own needs. Australia transported personnel to Southeast Asia. The United Kingdom conducted long-range maritime surveillance during the Falklands War. The Turkish Air Force used it for both military transport and humanitarian relief operations during the 1999 Marmara earthquake. C-130s were carrying supplies to the disaster zone from the very first hours. Japan established links between its island regions. Saudi Arabia ran desert operations. Brazil used it to reach deep into the Amazon. Each geography was different. The need was the same. And the remarkable thing was that most of these countries had entirely different climates, terrain, and operational conditions. Yet the same aircraft worked in all of them, in desert heat, in polar cold, in tropical rain. That is the highest praise that can be given to an engineering design. And most of these countries kept the aircraft in their inventories for decades, because finding an alternative to replace the C-130 was no easy task. No other aircraft offered this combination of short runway performance, payload capacity, ease of maintenance, and operational flexibility. Some countries tried. They evaluated different aircraft. In the end, they came back to the C-130s already in their fleet. Lockheed Martin never shut down the production line. From the first prototype in 1954 to the present day, the models evolved from A to B, from E to H, and finally to J. Avionics were updated. Engines became more efficient, but the fundamental design, high wing, 4 turboprops, rear ramp, reinforced landing gear, stayed the same. Because it worked. Sunset, AC-130, is approaching its home base after a long mission. The pilot adjusts the descent profile. The propeller sounds slow down. The landing gear, locked indicator light comes on. The aircraft glides toward the threshold. Wheels touch concrete. Reverse thrust kicks in. The aircraft slows and turns onto the taxiway. The engines shut down one by one. Number 4 first, then 3, 2, and finally, number 1. The propellers wind down to a stop. In the cockpit, the crew completes the checklist. Systems power down. Switches are turned to 0. The flight engineer records the final parameters. His ears are still ringing. The engine noise that had been going for hours has stopped, but his brain hasn't adjusted to the silence yet. He rolls his shoulders back, tilts his neck side to side. His body has been locked in the same position for hours. The captain rises from his seat. He looks out the cockpit window. At the far end of the runway, another Hercules is sitting. Its engines haven't started yet, but the cargo ramp is open. Loading is about to begin. The C-130 Hercules first flew in a different world. The Cold War was just beginning. The jet age was only taking shape. Since that day, wars have started and ended. Borders have shifted. Technology has become unrecognizable. But one aircraft is still flying. The same fuselage, the same 4 engines, the same rear ramp. From the first C-130A to today's C-130J Super Hercules, more than 2,000 aircraft have been built. Over 60 years of uninterrupted production, the longest produced military aircraft in the Western world. Even now, somewhere on the planet, a C-130 is either taking off or landing, racing toward a disaster or hauling supplies to a base, sliding to a stop on a glacier or lifting off from a desert airstrip. Some machines do just one job. Some leave their mark on an era. But very few manage to remain indispensable for over half a century, in every corner of the world, under every condition. The C-130 Hercules is one of those very few.